Hi, James here. This live stream has a special guest computer scientist, Maaike. It was the first time I've tried to have a guest on the live stream, and my poor computer couldn't really cope with all the video processing I was asking it to do live. I've uploaded this maths only edit anyway, even though the frame rate is really low and there's a bit of lag between the audio and the video. After this live stream, I changed some settings on my computer, so it's not going to be like this every week. I'm sorry for the lower quality than usual, and I hope you can still learn from this video. Okay, let's go.
So in this question, we have a cat and mouse game. We have a cat chasing a mouse, but we want to make sure that the mouse makes it to safety. And we're going to see in how many different ways the mouse can run from the cat while still getting to safety, basically. And we're interested in that number. And of course, there's a very simplified version where the cat and the mouse can only take integer steps, so steps of size 1. And so on my whiteboard, I'm not sure if you can see this. I have a little mouse. This is the mouse. And he's currently at place 3, right here. And his safety, this is the safety home. I didn't have a house magnet. That's at number 5. And here at point 0 is a cat, which my cat is a bear. I didn't have a cat. He starts at place 0 and starts chasing the mouse. And then the question is, how many ways can we move mouse and cat, and maybe cat again, without having the cat catching the mouse and the mouse getting to safety? So that is the setup of the question.
Part 1 asks, can we write down 5 valid games? It tells us there are 5, and it says that we should consider h equals 4 and m equals 2. Okay?
Yeah, so I forgot to say, they have letters for all of this. So m is where the mouse is, the position of the mouse on the number line. The starting position of the cat is always at 0. And h is the house, the safety.
Okay, so in this question, h is 4, and h is 4, the house is at 4, there it is, and the mouse is starting at 2. It's got a bit of a head start on the cat.
Yeah, and then we want to know how many possible ways of moving there are such that the mouse gets to safety. And well, we can immediately see that if the mouse just runs 2 steps, then it's to safety. So that's our first possibility, really. Mouse, mouse. I'm going to denote like that. But there's more possibilities. Because, of course, we can have the cat moving 1 place first. We can start with the cat. But then the cat can't move again, because then it will catch the mouse. So the mouse now has to move once. And then if it moves twice, it wins again. So that gives us another game. Cat, mouse, mouse. If I reverse that again, and start with cat, mouse. Another thing I could have done is move the cat, because there's now a space and he's not catching the mouse. So I can have a cat here, and then the mouse can get to safety. This already gets us up to 3 possibilities. Now to see the 2 that I've missed, but I've started with the cat here, but the mouse can also start. The mouse can walk once without winning immediately. And then the cat can move. Because if the mouse moves, then we're back into this, so we have to move the cat. And then the mouse can move again, win. Or, other possibility is mouse, cat, then we're back into this position. And then we move the cat the second time, before finally the mouse wins. There's a sort of systematic walkthrough through all of the possibilities, and I hope you could see that. I hope I wasn't in the way. It's a bit hard to see. explain why the number of games when the mouse starts one place back from the home is exactly home number -1. Well, what we notice in this setting, let me get my screen back, is as soon as the mouse moves, the game is over. So then the mouse has won and the game is over. But before the mouse makes that move, the cat can move any number of places from 0 all the way up to h-2. Because you can't move to the mouse because then he catches them. So yeah, the cat can move from 0 to h-2 number of moves, and then the mouse will move 1 as one of those. So that is a total of h-1 different games that you can play that way. So the question is asking about the specific setting where the mouse is either at 2 or at 1, and comparing those. So I'm going to start with the mouse at 1 to explain this question. Because when the mouse starts at 1, then the only way for it to not get caught is to move first. So our first play in the game has to be that the mouse moves. And well, from there on, if we now look at the setting, it's exactly the game where the mouse starts at 2. So the number of games in both cases is the same. Because there's no choice for the first move in the game where the mouse starts at 1.
Next part of the question looks really horrible. Look at all this. By considering the possible first moves of a game, so is this going to be like, so you were just telling me about the possible first moves in the case where there was only one possible first move.
Yeah.
And then there's this kind of...
Scary as it sounds.
Yeah, okay, I'm going to cut back to you.
Oh, I return to a more general setup here. And saying, well, in this case, there's 2 possible first moves. Either the mouse can move first, or the cat can move first. And the question is asking to consider both of those and then derive that long formula. But it's not really as scary as it looks. Because if the mouse moves first, like in the previous question, we noticed that if you then look at the setting, it's really the beginning setting of a new game, but then where the mouse has moved 1 from. So that is if mouse first, then we're in a setting where G is H and M plus 1. So the number of games where the mouse moves first in the original setting is exactly the number of games, the total games, where the mouse is 1 position further on. So that is half of the question. And you see this term in the question there.
Okay, so that's if I'm going to cut back to that. I'm going to cut back a point to it. Sorry. So that's this term, right? There. No.
Yeah.
H,
yeah.
M plus 1. That first one. So these are the cases where the mouse moves first. Okay.
Yes.
Thank you.
But then we have to consider if the cat moves first. So if the cat moves first, we're in this position here. I'm just going to erase this. But then if we look at the resulting situation, what we can really do is erase all those numbers here, because the cat always starts at 0, and then renumber.
Oh.
And then what you see is that this is the starting position where both the mouse and the home are 1 less, because this is the old numbering was this. So we see that both the mouse and the house have moved 1 position closer to the cat by the cat moving.
Oh, right.
There's a thing going on there.
It's that relabeling. Hang on, let's just point at the other. Let's just, for completeness, I'm going to point at the other term in the equation. Well, that's this term. So I suppose it's saying if that relabeling seems quite clever. I think if you move the idea that if you move the cat, then even though we defined it to have the cat, defined the problem to have the cat starting at 0, then we move the cat and it's not at 0 anymore, but we can relabel everything and think about the new problem of it starting there at 0. I think that's quite clever. Okay, I'm going to quickly label up on this one just to sort of drive the point home. This is mouse moves first. These are the cases where the mouse moves first, and these are the cases where the cat moves first. And these ones, Mike is thinking about a clever relabeling.
Yes.
Yeah, that's the problem. Okay.
So what we've known from, I need to make sure I need to refer to the right questions. So from question 3, we know that this bottom row here is going to be exactly the same as the row on top, because we know that this is H and this is M, and we know that H1 is the same as H2 from question 3. So I can copy this 2 down here already. And then from question 4, I know this relationship between, if I want to compute this square here, I know that GHM is GHM plus 1, that's that one, plus GH minus 1, M minus 1, that's that one. So I'm making this sort of shape where I take these 2 numbers, add them together, and then I get this one. That is what I got from question 4.
Wait,
and
that's like thinking about the recursion as a shape, like a geometrical thing.
Yeah.
That's good. That's nice.
So then I can copy it down here again because of question 3. And then I'm going to move up here. And again, I'm using this shape that I'm taking this one and this one, add them together to get this one here. And then for the one below it, I have to do that again. I'm taking the 9 and the 5 and add them together. And then I copy down again because of question 3. And copy that down here. And yeah, I'm continuing that way. So I have 9 and 5 here. And then to get this here, I add 14 and 14, 28. I add 28 and 14. And finally, I copy down.
Okay, and you get 42 at the end. Lovely.
The answer. So we have a recursively defined function, which previous question sort of gave you a feel of how you could get a recursive function out of a real life situation. And here the function is already given to us. And now the question is mainly about computing some actual values for that function. And well, what you usually do is you just give it to a computer. But this question gives you a feel for how the computer would actually solve a recursive function. So it's to give you a feel about how they work and how you get an actual value out of them, which is usually just keep on going, don't panic, and write every step out. So we want to compute f of 5. Is that visible? Yes.
That looks okay to me, just about. I don't know if you... Yeah.
Oh, slightly bigger. Slightly bigger. F of 5.
Great.
Now, 5 is odd, so the equation tells us that it is equal to 2 times f of 5 minus 1, and that is 4. That is the bottom of the 3, the lowest of the 3. If n is odd, this is what we get. And then we just continue writing it out. Now we want to know what f of 4 is. Well, 4 is even, so f of 4 will be f of n divided by 2. So that will be f of 2 squared. That's what the equation says. So here I have f of 4, and f of 4 is n divided by, so 4 divided by 2, which is 2, and that squared.
I'm going to quickly cut to the equation and point at what you've used there. Sorry, just in case. I saw you were pointing at it, so I want to point at it. Is this first one 2 times f of 4 from this line? And then because 4 is even, Mike is using the previous line here, f of 4 is f of whatever that is, squared. Sorry.
And this is the point where you don't panic and just carry on. This f of 2 is now of interest. So we had this squared bit, and now I want to know f of 2. Well, 2 is even, so f of 2 is f of 2 divided by 2 is 1 squared. There's a lot of brackets there. That's a bit scary, so I'm going to simplify that a bit. So I have a squared over here and a squared over here. I can simplify that to f of 1 to the power of 4. That makes it slightly less scary. So that is just so that I don't get caught in a flurry of brackets. And then we breathe in and out and carry on. With f of 1, well, 1 is odd, so I can use the rule for odd again. That's 2 times whatever it's going to be to the power of 4. And then I need to insert f of 1. Well, f of 1 is going to be 2 times f 1 minus 1 is f0. And notice how I first set up the whole framing here. So I did the 2 times that I had and the brackets and the 4, and then I just insert that bit. I rewrite this f1 there.
Lovely.
And then I have a bit more to go. So f0, that is good. f0 is given, that is 1. So I can insert that. So I do the whole framing again. 2 times. That is my framing here. And now I'm just going to replace this f of 0 by its value, which is given in the question, that is 1. And now I just need to work out what this value is. So that is 2 times 1, that is 2. That is 2 times 2 to the power of 4. 2 to the power of 4 is 16. I'm running out of space here, so I'm just going to do that. That is 2 times 16, and that is 32.
Nice. The question introduces this idea of recursion depth next. Is that an actual thing?
Yeah.
Okay. And it's the number of other integers m, such that the value f of m is calculated whilst computing the value for a particular f of n. They give us an example, and they ask us to do another example, to think about this calculation we just did for f of 5, and to work out the recursion depth of that. Do you want to show us on the whiteboard?
Yeah, so the recursion depth is really the calls you make. So here we said f of 5 is something times f of 4. So there we're calling the function again with a new value. And the recursion depth is saying how many times we do that. And in this question, we're quite lucky because the example already tells us that the recursion depth of 4 is 3. And the first thing we're calling here is f4. So the recursion depth of 5 is really just 1 plus the 1 from 4, because we're making one extra call, namely the function of 4. So the depth is 4 in this case.
Amazing, and I love that you're using the number in the question as well. Let's hang on. I want to point at that because people might not have spotted. I didn't read it out. They tell us the recursion depth of f of 4. So to work out f of 4, you need to call 3 other values to put into f. So Maaike's used that to shortcut some of the working. I guess you've got, if the recursion depth here is 4, does that mean you've got 4 other numbers inside f's on your whiteboard?
Yes. So I have 4, 2, 1, and 0.
Right. Okay. And it's those are the four other numbers that.
Those are the ones
the recursion depth before.
So we have g of 5. Well, 5 is odd, so we're going to look at what happens then. It says that is 1 plus g of 4. Well then, 4 is even, so the instruction says that this is now 1 plus g of 2, because now I have to divide by 2. That is 4 is even. I hope this is still,
Yep, looks good.
And I'm just going to continue, breathe in, breathe out, copy my structure. 1 plus 1 plus something. And now G2. I've copied the structure around and I'm going to do G2. Well, that is 1 plus g of 1. So I again have to divide 2 by 2, then I get g1. That is because 2 is even. That's what the instructions tell me to do. And I'm just continuing. 1 plus 1 plus. Because it's only addition, I don't really need those brackets. Leave those out just to make it easier to read. 1 plus 1 plus 1 plus 1 plus. And now it's g of 1. Well, 1 is odd, so that would give me 1 plus g of 0, because 0 is 1 minus 1. That is 1 is odd. And now g0 is given. This is 1 plus 1 plus 1 plus 1 plus. G of 0 is 0 in this case. And then I can compute the whole sum, which is 1, 2, 3, 4. Well, if I haven't made any mistakes. So we're asked to compute g of 2 to the power of k. Well, 2 to the power of k is even. Is that visible with the reflection?
Yeah, the reflection's in an unfortunate place, but I think we know you've written g of 2 to the k.
Yeah. Yeah, sorry, I can't really.
Nah, it's fine.
Well, because 2 to the k is even, it will be equal to 1 plus g of 2 to the k divided by 2, which will be 2 to the k minus 1. That is interesting. I'm going to write it out one more. Because 2 to the k minus 1 is again even if k is big enough. That'll be 1 plus 1 plus g to the 2 to the k minus 1 divided by 2, which will be 2 to the k minus 2. And this one continues until we reach 2 to the power of 0. So we're just going to have a big sum of 1s. And then we're going to have a g 2 to the power of 0, which I can also write as instead of 2 to the power 0, I'm going to write that as k minus k. As you see, we have k minus 1, k minus 2. We're going to do that all the way to k minus k. And then this is 1, so that will be g of 1. So if I'm going to write that again, I have a bunch of 1s, and then plus g of 1. And I know that this is going to be 1 plus g of 0 from the function. So that is just 1, because g of 0 is 0. So that is 1. But now the question is really, how many 1s do we have over here? Well, for each iteration, I'm adding 1. So when I went from k to k minus 1, I got a 1 on the front. And then for k minus 2, I have 2 1s at the front. So then for k minus k, I will have k 1s here. So this all sums to k, and then this last bit is 1. So the final answer will be k plus 1. G of 2 to the L plus 2 to the K. But if I'm just going to start mindlessly again and just do 1 or 2 iterations to just see what happens. So this is even, because I'm adding 2 even numbers, that's even. So that is going to be 1 plus this number divided by 2. And this number divided by 2 will just be 2 to the power of L minus 1 plus 2 to the power of K minus 1. Because if I divide 2 to the L plus 2 to the K by 2, I have to divide both by 2, and that lowers their exponents by 1. But if I do just the second one, just to really know what's going on, that'll be 1. This is again even, so just the same thing happens. 1 plus g of, I have to divide both by 2, so that'll be L minus 2 plus 2 to the power of K minus 2. And now I can be cleverer than a computer again. I can see where this goes. This will go on until one of these will become 2 to the power of 1. And no, because L is bigger than K, but K is going to reach that first. So I have this whole bunch of 1s at the start. And then I'm going to hit g of 2 to the power of L minus K plus 2 to the power of K minus K. And then by our previous reasoning, I already know that these are K1s. That's what we did in the previous question. Mm-hmm. And now this is an odd number, because this is really 2 to the power of L minus K plus 1. Then we're going to do the mindless step again. So we have K1, so that sums to K. Plus, and now because this is an odd number, it tells me it's 1 plus g of 2 to the L minus K plus 1 minus 1. So that'll be just g of 2 to the power of L minus K. And now we know from the previous question what this is. That'll be K plus 1 plus, from the previous question, 2 to the L minus K plus 1.
Do you want 2 to the L minus K? Or do you want...
Sorry.
No, that's good.
Nope. That is going to be L minus K plus 1. Sorry.
Yeah.
So that simplifies a little bit, doesn't it? Because the k's, yeah.
Yeah, so we have a k here and a k there that we cancel out. So that is going to be L plus 1 plus 1 is L plus 2. Yeah.
Nice.
I hope if I haven't made any further mistakes.
Yeah, no, I agree. So this is L plus 2. Why is g of n, this is relating it to the previous thing, why is g of n equal to the recursion depth of f of n?
Yeah, so this is where we really look at the function and interpret it, what it means really. And we've already noticed that it has the same recursive calls as f. So if n is even, then you divide the number by 2. And if it's odd, you take the previous one. But instead of doing all those calculations that f does, g just adds 1. So it's really a counting function. It counts how many recursive calls you're making. Because if n is 0, then from f, we have immediately the answer. So we make 0 recursive calls. And if n is even, then we make 1 recursive call to get f of n divided by 2, and then plus however many recursive calls that function takes. So that's why there's 1 plus g of n divided by 2. And same for when n is odd, is we make 1 recursive call to get f of n minus 1, plus however many recursive calls it takes to compute that one. So, yeah.